power cycle, which we already discussed in the previous class, which is the gas turbines. Okay, so today we will practice some sort of question related to gas power cycle and the Brayton cycle. Okay, so this is the statement of the question, first question. So you have to read the statement. Okay, another important point is that today one student point out that in the previous lecture of the dual cycle, if you shown the screen is shown over there, so the formula which is T5 over T4. Okay, so this is I think lecture number 15 is mentioned over wrong, in this slide is wrong. Okay, so it is T4 over T5. Okay, and rest of the question is right, whatever the answer in this question we have generated. Okay, only T4 over T5 you have to correct it. Okay, it is not T5 over T4. Okay, so kindly and do also double check all the question whenever I solve, because I am solving and I am not looking for the solution at that time. Okay, so that's why you have to check the solution after this, that the answers are right, or if there is any wrong thing which I have mentioned, then you have to point it out. Okay. Okay, so now it is a question which is mentioned over there for today lecture. So air enters a compressor of gas turbine power plant operating on a Brayton cycle at pressure 101.325 kilopascal and 27 degrees Celsius. So it's mean that P1 over T1 is mentioned in your question. The pressure ratio in the cycle, so it is the ratio for the maximum pressure to minimum pressure. Okay, 6, or we can say it is RP. Calculate the maximum temperature in the cycle. So maximum temperature lie at the point number 3, which is the inlet of your turbine, or you can say it will be an outlet of your combustion chamber. Okay, and assume WT, that work for the turbine, is equal to 2.5 times of WC, where WT and WC are the turbines and the compressor work respectively. Okay, so this is the problem statement. So you have to note down the data, then we'll move towards the solution. Okay, so starting from the TS diagram for the ideal Brayton cycle, so I will just quickly draw the TS diagram over there. Okay, so in the question it is mentioned that P1 is known to you for the value 101.325 kilopascal, and then the T1 is also known to you, which is 27 degrees Celsius, or you can convert it into the Kelvin, so it will be 300 Kelvin value. Okay, so now the first part we have to find the maximum temperature. So maximum temperature is at point number 3. Okay, so main target is to find the T3. Okay, so we can start from the one isentropic relation for process 1 to 2. Okay, so isentropic relation, so it is the part number A. T2 over T1 is equal to P2 by P1 K minus 1 over K. Okay, so this is the relation valid for the isentropic process, as we discussed in the first lecture of your gas power cycle. And I have already told you that RP, which is the pressure ratio, is the ratio for maximum pressure over minimum pressure. Okay, or you can also say that it will be equal to P2, because P2 is equal to P3 and P1 is equal to P4. Okay, it is a constant pressure process. Okay, so from here I can easily find that T2 is equal to, because T1 is known to us, which is 300 Kelvin, and P2 or P1 is the pressure ratio which is mentioned in your question. Okay, and from question it is mentioned is 6, and K is the specific heat ratio for air. Okay, so you have to solve it, and then it will be T2 becomes 500.4 Kelvin. Okay, so now T2 is known to us. So moving towards the T3. Okay, so for T3 we can simply use another relation of isentropic process for 3 to 4. Okay, because 3 to 4 is also isentropic process. So from here I can say that T3 over T4 is equal to Rp. Okay, so again it is P2 P4 over P3 over P4. Okay, Rp K minus 1 over K. Okay, so T4 we have to find okay, so from here I can say that T4 is equal to T3, and if just I simply put the value of Rp, which is 6, and I can solve it, it will be equal to 1.668. Okay, so now T4 is given to us in term of T3. Okay, so our main target is to find T3. So now in the question it is mentioned that assume work for your turbine, that is the output work of the turbine, is equal to 2.5 times of the compressor work, which is the supplied work through your compressor. Okay, so we can use that condition which is mentioned in your problem. Wt is equal to 2.5 W compressor. Okay, so from here I can easily say that because if you can notice that turbine is between 3 to 4. Okay, and your compressor is between 2 to 1. Okay, so from here I can simply use that MCP T3 minus T4, because turbine is there, is equal to 2.5 WC is the compressor, and CP mass flow rate through the compressor, and CP and T2 minus T1. Okay, so if you can notice over there that because we are talking about turbine, okay, so if we can say that it will be equal to H2 minus H1, sorry, for the compressor. Okay, so you already know that delta H is equal to MCP delta T. Okay, so from this relation I have just put these value MCP T3 minus T4, MCP T2 minus T1. Okay, so now M can be eliminated because the mass flow rate is the same. Okay, CP value you can also eliminate. Okay, because CP for the air is same. Okay, so from here if I can solve it for, okay, so simply I have to put the value of T4 first in this equation, so which is T3 by 1.668. Okay, and then T2 value is known to us from this part, and T1 value is known to us from the problem statement, which is 300 Kelvin. Okay, so now if I can solve this equation for value of T3, it becomes equal to 1251 Kelvin. Okay, so this you have to solve it by yourself. So this is the part number A, where we have to find the maximum temperature for your Brayton cycle. Okay, so if you have any question, you can ask me, and you have to note down the solution. Then we'll move towards the part B. Okay, so for the part number B, the required thing is that we have to find efficiency of the cycle. Okay, so for efficiency, you already know that for efficiency, we have W net over Q in. Okay, so from here we can simply say that MCP T3 minus T2 minus MCP T2 minus T1, which is the compressor work, okay, and which is divided by MCP T3 minus T2. Okay, so this is the another form of the equation. Okay, so if you can use another relation, which is the simplified one, you can also use, which we have developed in the previous lecture. Okay, so from this we have the value of T2 with us, T1 with us, and we also know the value of T3 from part A. Okay, so now T4 is sorry, in this one T3 minus T4. Okay, because this is the turbine work. Okay, so turbine is between 3 to 4, so we do not have the value of T4. Okay, so first we have to find the value of T4, then we can simply use plug the value in this equation and we can get the efficiency of your Brayton cycle. Okay, so now T4 is equal to T3 over 1.668. Okay, so this relation come from your part A. Okay, so which we already see that T4 is equal to T3 by 1.668. So T3 is known to us. Okay, so simply you have to plug the value of T3. So it will be 1251 from the previous part A and 1.668. Okay, so from here we can easily find the T4, which is 750 Kelvin. Okay, so now we have the value of all the temperature with us, so simply we can put in this efficiency equation and we can find the efficiency of Brayton cycle as 0.4, or we can say it will be 40%. Okay, this is a solution of part number B. Okay, so another thing is that you can use the Brayton cycle, because we are working on the air standard assumption, so you can simply say that 1 minus 1 over Rp K minus 1 over K. Okay, so this relation you can also use in order to find the thermal efficiency of your cycle, because Rp is known to you from the question, so specific heat ratio value is known to you, and this you can use also. Okay, so you have to note it now, then we move towards the second question. Okay, so now we already discussed the ideal case of the Brayton cycle, but you already know that there are irreversibilities associated with the compressor and also with the turbine. Okay, so it's mean that your entropy is not constant in your actual cycle. Okay, so as we see in the Rankine cycle also. Okay, so here, but only difference is that here is the pump in your Rankine cycle. Now we have the compressor. Okay, so now we can use actual values, which is because we have to shift the isentropic process towards the increase in entropy values, because if there are irreversibility, you already know that the irreversibilities result in the increase in entropy. Okay, so for that we have to develop the TS diagram over there. Okay, so the TS diagram is previously we used 2s point and 4s point. Okay, so now due to the irreversibility, this point 2s will be shifted towards the right side of your TS diagram, which is towards the increase in entropy, and so 2A is moving towards the right, and also the 4S point is also moving towards the right side, okay, and it is shifted towards the 4A. Okay, so now your 2A, so this term 2A to 3 is your Q in, okay, so and this is your actual heat addition now, okay, and the actual heat rejection is now from 4A. So this is your actual heat rejection now. Okay, so if in the question it is mentioned you have to find the Q in for the actual gas turbines. Okay, so you have to find the value of 2A first, and then you can use the value of 3. Okay, or either it will be a variable specific problem. So then you have to find the efficiency enthalpy value at H2A point. Okay, the similar thing if we have to find the Q out, which is the actual Q out. Okay, so you have to consider this 4A point. Okay, rather than 4S point. Okay, so as we discussed in the Rankine cycle also, whenever there will be irreversibility, so we have to find the efficiency of your isentropic efficiency of the compressor now and isentropic efficiency of the turbine. Okay, so isentropic efficiency of compressor is the WS, which is the isentropic work, and WA is the actual work. So it is the ratio of isentropic work over actual work. Okay, and make sure that this isentropic work, okay, so for the compressor is the small and this term will be the large. Okay, so then we will get the efficiency of it. Okay, so similar thing, isentropic efficiency of the turbine. So here we have to keep the lower term above. Okay, so WA, which is the actual turbine work. So it's mean that whenever there be the irreversibility, so it will result in the decrease in turbine work. Okay, so that's why this term will be lower. Okay, and WS is the isentropic work. Okay, so this term will be the bigger. Okay, so this is the relation which we already discussed in the Rankine cycle as well. Okay, so similar thing we have to use this whenever we have to analyze the actual gas turbine Brayton cycle. जी
सर सर ग्राफ में सर H3 की वैल्यू सर डिफरेंट नहीं हो रही आइडियल की और एक्चुअल की
नहीं ये आपको बताया हुआ है आपके पास ये वैल्यू आपके पास आप कह रहे हैं ओके ये जो आपको डॉटेड लाइन बताई हुई है ये आपके पास बताया हुआ है प्रेशर ड्रॉप हीट एडिशन okay so this is the only thing that we have defined that pressure drop over there. Okay, so if you have to find the H3 value, okay, so it is mentioned in your question that this 3 point which is the turbine inlet pressure is this one, or turbine inlet pressure is temperature is this one, so you can easily find the value of enthalpy over there. Okay, okay, so this point is either given in your
यस
question or okay, so you have to correlate with it. So we will see one question, then you can understand it. Okay, so similar thing, there will be a pressure drop during the heat rejection process, so that's why this curve will be shifted towards the uh, above side. Okay, so this is the example I think 9-6, okay, from your book. Okay, so in this example we have to use the same data which is from example 9-5. So in the example 9-5 we already solved this problem by using the isentropic isentropic process. Okay, so mean there will be isentropic compression and isentropic expansion take place. Okay, so we have to use the same data. So you have to read it, and that in example 9-5 assume a compressor efficiency. So we are talking about the isentropic efficiency of the compressor and isentropic efficiency of the turbine 85%. So what you have to determine back work ratio, the fraction of the work which is delivered back towards the compressor, the thermal efficiency, and turbine exit temperature of the gas turbine cycle. Okay, so this we have to find. Okay, so I will quickly draw the TS diagram first. Okay, an important thing is that whenever you have to solve, make sure that you have to make a correct TS diagram. Okay, otherwise it will be very difficult uh, that you can solve it correctly. Okay. we are assuming that there will be isentropic efficiency of your turbine and compressor. So it's mean that this point will be shifted towards your point number 2a. Okay, and this point which is previously at point number 3. Okay, so you can say it will be shifted towards your 4a point. Okay, so simply we can, just because there will be, whenever there will be irreversibility, it will be associated with the turbine or your compressor. Okay, so it's mean that this will be increase in entropy. Okay, so this is the TS diagram for you cycle. So now we will see that how we can use this type of relations in order to solve this type of problem. Okay, so simply for first part, okay, so we have to find the back work ratio. So as you already know that back work ratio is the BWR, is the ratio for your compressor over turbine. Okay, so here we are talking about the actual compressor work and the actual turbine work. So in the previous example 9-5, we have already find the isentropic work for your compressor and isentropic work for your turbine as well. Okay, so simply we have to find first turbine work, which is the actual one. Okay, so you can say that it will be equal to turbine out. Okay, and we simply use the relation which we already see in the previous slide. So efficiency, isentropic efficiency of the turbine, and WS. Okay, so this is WS is basically the isentropic work which we already find in the example 9-5. Okay, so we are using some data from the previous example. So isentropic efficiency is given in your question 0.85, and WS we have already found in the example 9-5 in the previous lecture. So it is 606 point. Okay, so if I can solve it, it turns out to be. Okay, so now this is actual turbine work is known to us. So similar thing we have to apply for the compressor work also. Okay, so for the compressor work, okay, so simply we can find out because it is the in. So compressor in, I can just denote isentropic work over efficiency of your compressor. Okay, so WS is mentioned from the previous example 9-5 because this is isentropic work, and isentropic efficiency is 0.8. Okay, so from here we will get the actual compressor work also. So 305.2 kilojoule per kg. Okay, so now we have the actual compressor and actual turbine work, so we can simply use the back work ratio equation, and we can put the values 305.2 and 515.61, and that turns out to be 0.592, or you can say 59.2 percent. Okay, for your back work ratio, which is the actual back work ratio. Okay, so if you compare with the previous example, in the previous example it is 40.3%. Okay, so this increase is due to the irreversibility that occur within the compressor and the turbine. Okay, so that's why it will be, because in this way we get the higher back work ratio in the actual cycle. Okay, so you have to note down the part A, then we'll move towards the part B. If you have any question, you can also ask me. Okay, so this is the TS diagram which is taken from your book example. Okay, so it is mentioned over there, it is clearly shown over there. Okay, so now in the part number B, we have to find the efficiency. Okay, so for efficiency we need to find W net or Q in. Okay, so now Q in, we are talking about the actual key Q in. So actual Q in is between 2A and 3. Okay, so for actual Q in, first we need to find that Q in is equal to H3 minus H2A. Okay, so now it is not 2S. Okay, so we do not have the value of 2A with us. Okay, so H3 value is known to us from the previous example. Okay, but here we have to find the H2A. Okay, so for H2A we can simply use the relation which is the compressor in. Okay, so which is the actual compressor in is equal to H2A minus H1. Okay, because H1 is known to us and WC1 we have already find in the previous part A. Okay, so simply what you have to do is you have to solve it for H2A, and H2A is equal to H1 plus W compressor in. Okay, so from just we have to put the value, so which is 300.19 for H1 value, this taken from your previous example 9-5, and the compressor in from part A, so it will be 305.2, and H2A will be 605.39 kilojoule per kg. Okay, so now we can easily put the value in the Q in, okay, which is the H3 minus H2A. So H3 value is from the previous example 1395.97, okay, which is the same one, and H2A value is 605.39. Okay, so if you can simply solve it, it turns out to be 790.58 kilojoule per kg. Okay, so now the actual Qn is known to us. So now we have W net. Okay, so W net is simply W out, which is the actual turbine out, minus W in. Okay, so W in is basically the compressor. Okay, because we have to supply it from the towards the compressor. Okay, so W out is 515.61. Okay, so which we already find in the part A, and W compressor actual we have already find, which is 305.2. Okay, so if we can solve it, it turns out to be 210.41 kilojoule per kg. Okay, so now we have W net actual and Q in actual. So simply you have to put the value in the efficiency equation, and it is 210.41, and Q actual is 790.58. Okay, and if you can solve it, it turns out to be 26.6%. Okay, so if you can just compare with the previous example, the value is 42.6%. Okay, so it's mean that there is a drop in efficiency due to the irreversibility associated with the compressor and turbine. Okay, so this is the solution of part A. So you have to note it down, then move towards the part C. Okay, so in the part number C, what we have to find is we have to find the exit temperature of the gas turbine. So it's mean we are interested in to find point number 4A. Okay, so for 4A, first we need the value of H4A. Okay, so we already know that for W turbine is equal to H3 minus H4A. Okay, so for here from this equation we can simply say that H4A is equal to H3 minus W turbine. Okay, so this is the actual turbine. Okay, so H3 value we already have with us from the previous example. So H1395.97 minus 515.61. Okay, so from here we can get the H4A value, which is the actual enthalpy value. Okay, so now easily we can use this H4A value, and you can simply go to table A17, okay, and do the interpolation by using this reference value H4A, and you will get the value of H4A, which is the actual exit temperature. It turns out to be 853 Kelvin. Okay, so this is the solution for part number C. So this is the required thing. You have to find the exit temperature, which is the actual exit temperature. Okay, so if you have any question, you can ask me, and then we'll move towards the next question.
सर ये टेम्परेचर इंटरपोलेशन से फाइंड करेंगे।
जी, टेम्परेचर इंटरपोलेशन से आपने फाइंड करना है। टेबल A17 में जाके आपने इंटरपोलेशन करनी है बाय यूजिंग दिस रेफरेंस वैल्यू H4A. So you will easily get the T4A.
सर जब हम कैलकुलेशन करते हैं सर वो पॉइंट्स में काफी फर्क आता है कैलकुलेटर से और जो एग्जांपल के होते हैं सर उसका तो मुझे
नहीं
लिखते
मैं
का सर जैसे कि 853 है 850 आ जाता है सर या 857 आ जाता है समटाइम।
नहीं, उससे कोई इशू नहीं होता, ठीक है, क्योंकि आपका जो बुक के अंदर हुआ हुआ है वो EES सॉफ्टवेयर होता है हमारा थर्मोडायनेमिक्स का, उसके थ्रू कैलकुलेट किया हुआ होता है। तो आपका अगर कैलकुलेटर से थोड़ा डेविएशन आ रहा है तो उसको कोई इशू नहीं है, मैं उसको कंसीडर कर लूँगा, क्योंकि मुझे भी पता है इंटरपोलेशन आप अगर सॉल्व करेंगे तो उससे थोड़ा बहुत आपके ऊपर नीचे वैल्यू चली जाती है। ओके, तो उससे कोई फ़र्क नहीं पड़ता इतना। Okay, and most of the time, if in the question it is mentioned that you have to provide the interpolation and you have to use the interpolation, and you have no time, for example, in the exam, there is the time left is 5 minutes and you have to do the interpolation. So rather than you have to use the interpolation, you can just judge that this value will lies in between these 2 points. Okay, so you can assume any value and you can just write that this is by interpolation. I am assuming this thing. Okay, so still I will consider it. Okay, so I have to just look for it that you know the procedure. Okay, so you do not have to go for the full interpolation if you do not have the time in the paper. Okay, so now here is another question. Okay, so this is also related to the actual Brayton cycle. So in a gas turbine plant working on a Brayton cycle, the air is at inlet is 27 degrees Celsius and 0.1 megapascal. So P1 and T1 is known to you. The pressure ratio is 6.25, so RP value is known to you. The maximum temperature is 800 degrees Celsius, so T3 is known to you. And the turbine and compressor efficiency are each 80%, so both isentropic efficiencies are given. Find compressor work, turbine work, heat supply, cycle efficiency, turbine exhaust temperature. Okay, and you have to just consider that mass of the air may be considered as 1. Okay, so this is the question. Okay, so now we will use this data to solve the question. Okay, so you have to note it down, then we'll move towards the solution. Okay, so for the part number A, what we are interested in, we are interested in to find the compressor work. Okay, so which is between 2A and 1. Okay, so for compressor work, we can say that W compressor is equal to MCP T2A minus T1. Okay, so now in this question, we have to find T2A first because T1 is known to us. CP value is also known to us because it is air, and then okay, so and the mass flow rate is also known, which is 1. Okay, so simply first we have to find the value of T2A. Okay, so for T2A, we use the compressor, which is T2 minus T1, T2A minus T1. Okay, so this is the relation for your compressor work. If I am assuming that it is the air standard assumption, okay, so then we have to use this type of relation also. Okay, I hope there will be no confusion that where this relation come from. Okay, because I already know told you that whenever we have to, that delta H is equal to MCP delta T. Okay, so simply you have to use this relation and you can plug in the value of compressor efficiency and then you can find this type of relation. Okay, so now we have to find the value of T2 first because T2 is not known to us, T1 is known to us, and what we are interested in to find the T2A. Okay, so first we have to find T2. Okay, so simply I can apply one isentropic relation for process 1 to 2. Okay, so T2 or T1, which is the isentropic process. Okay, or I can say it will be 2s. Okay, so that you will get not confused. Okay, so now the pressure ratio is known to you from the question, which is 6.25. Okay, so simply you have to put the value and you can easily find the value of T2s, which is 300 into whatever the RP value. So you can solve it by yourself. It will be 1.688. Okay, and it turns out to be 506.4 Kelvin. Okay, so now this is the 2s value. So now we have the 2s with us, so we can easily solve this equation because this value is known to us. So we can get the value of 2a by solving. You can say it is equation number 1 or anything. Okay, so T2a become 558 Kelvin. Okay, so this you have to solve it by yourself. Okay, so now we have the value of 2a with us, so simply you have to put the value in this equation, which is the W compressor. Okay, so because this is 1 m, CP value is 1.005, T2A value is 558 Kelvin, and T1 value is 300 Kelvin from your problem statement. Okay, so from here you can easily find the compressor work, which turns out to be 259.29 kilojoule per kg. Okay, so this is the solution for your part number A. Okay, so you have to note it down and move towards the next part. Okay, so in the second thing which is required is the turbine work. Okay, so turbine work, so simply it's the same procedure. So turbine work is equal to MCP T3 minus T4A. Okay, so now we have to find the T4A first. Okay, so T4A is again find from the isentropic efficiency of the turbine equation, which is T3 minus T4A. divided by T3 minus T4s. Okay, so simply you have to find the first T4s. Okay, so same procedure which we already discussed in the previous example. So you have to apply one isentropic relation for finding the T4s first. Okay, so I can say T3 over T4s is equal to P3 over P4 K minus 1 over K. Okay, so from here I can use I can just rearrange it, and it turns out to be T4s value, because P3 or P4 is known to us from the question. Okay, so you have to solve it by yourself. T4s become, and T3 is already known to us, okay, from the question, because it is mentioned that it is 800 degrees Celsius, so it is 1073 Kelvin. Okay, so for solving it, it turns out to be 635.66 Kelvin for the value of H4s, T4s. Sorry. Okay, so now simply I can put this T4s over there, and efficiency of turbine is known to us. So by solving it, it turns out to be the T4A become 723.13 Kelvin. Okay, so simply I have to use this equation, and you can solve it by yourself, and it will get 723.13 Kelvin. Okay, so now we have all the values. So simply you have to put the value of T4 into this equation, which is turbine work. Okay, so M is 1.005, and T3 value is 1073, which is given in your problem statement, and T4A value we just have found in the previous part. So simply you have to solve it, and it will get 351.6 kilojoule per kg. Okay, so this is the turbine work, which is required in your question. Okay, so you have to note it down and move towards the next part. Okay, and another thing is that this part is also asked in the question, that you have to find turbine exhaust temperature. Okay, so this is the T4 A. Okay, so this is also required in your question. Okay, so this is also the one answer. Okay, so now another thing which we have to find is the Q supplied. Okay, so which means that we have to find the Q in between 2s and 2A and 3. Okay, so simply we can say that Q in is equal to MCP T3 minus T2A. Okay, so T2A value is known to us, T3 value is known to us, CP value is known to us. So simply you can put the values, and you will get the value of Q in 1073 from the question, and 558 from the previous part. Okay, so simply you can use this relation, which is turns out to be 517.57 kilojoule per kg of your Q supplied. Okay, so now one thing which is left is that to find the efficiency of the cycle. So efficiency of the cycle is simply W net over Q in. Okay, so W net, you can simply say that turbine minus compressor, which is the actual compressor and turbine work. Okay, so we already find it, and Q in, which is 517. So 351.6 is the turbine work, and compressor work, which is the actual compressor work, is 259.29 okay, and Qn is 517.57. Okay, so you have to solve it and you will get the value 0.1783. It will be equal to 17.83% of your compressor efficiency. Okay, so this is the solution for this type of question. Okay, so if you have any question, you can ask me or you can note down the solution, and then we will just stop at this point. Okay, so here is the question which you have to solve it by yourself. Okay, so it is the same question which we already solved in the start of this lecture. Okay, so related to ideal gas Brayton cycle. So